Welcome back to ECE 501B. Homework 6 is due tonight. Hopefully that doesn't surprise you. And the next thing that better not surprise you is our exam. Exam number 2 is scheduled for Wednesday. And we'll talk a little bit, that's how we'll start today, is talking about the process for exam number 2. But there is review material on the D2L website. Hopefully you've found that, or you know where to look if you're interested in that material. But real briefly, it's homeworks 4, 5, and 6, and chapters 5 and the first part of chapter 6 in the second edition of the textbook. Today what I want to do is move beyond exam number 2 material, and that is to talk or recap what we've talked about already, which is the adjoint operator and self-adjoint operators. And then we will look at a very simple linear map, and by simple I mean a matrix or a matrix representation that's really complex. It's a 1-by-1 matrix or a scalar, and we will then infer what that translates into or how that generalizes, and then we will create this table of associations with what numbers, complex number, a complex conjugate, real, what those translate into or generalize to as far as linear maps, so that when you hear a self-adjoint map, you can start to think about maybe a scalar version of that to give you a better feel for what's going on. Then we will state some propositions and corollaries for self-adjoint maps. We will talk about normal operators, and normal operators are different from self-adjoint operators. In a normal operator, the operator and its adjoint commute, which really just means that T dagger is equal to T dagger T. Now, if you have a self-adjoint operator, obviously that implies that it's a normal operator, but you don't have the opposite. A normal operator is not necessarily a self-adjoint operator. Then we will talk about this defining normal operators through the norm, and essentially this linear map applied to any vector, its norm is equivalent to the adjoint of that map applied to that same vector's norm. Then we will start looking at the eigenvalues and eigenvectors of these maps and their adjoints. And that now, once we have that, we can start talking about normal operators and distinct eigenvalues. That now gives us orthogonal eigenvectors, not linearly independent. If we had distinct eigenvalues for a linear map, then that gives us linearly independent eigenvectors. Now, if we have a normal operator, which is a little bit more specific than just a general operator, now if we have distinct eigenvalues, those eigenvectors are orthogonal, not just linearly independent. And then we will look at some spectral theorems, and it's really depending on which inner product space we are working on, whether it's complex inner product space or a real inner product space, that will lead to a different spectral theorem. Let's then start by telling you what I'm expecting for exam number 2 in terms of the process. I've added, I think, one more sheet of notes, so that means another front and back. You have 3 pages, and hopefully you don't have to reinvent all 3 pages. Maybe you still have the 1 or 2 that you had for the first exam, but you can now add to that. You can bring a calculator, something to write with. You need to demonstrate what you know, and I think the only way to do that is by writing. And there is no textbook, class notes, cell phones, or computers allowed. Topics, it's really chapter 5 and 6, roughly. Chapter 5 is dealing with eigenvalues and eigenvectors, and chapter 6 is inner product spaces, and in particular inner products and what that means or how those can be used or defined. Now you'll probably ask, well, do we have to know stuff from the first exam? Yes, you basically do, because everything is building on the first few chapters of the book. We need vectors, we need spanning, we need all of those concepts in order to move forward into chapters 5 and 6, but the questions will be focused on the new material that we are dealing with or working on in chapters 5 and 6. And that then is homeworks 4, 5, and 6, and you need to be able to apply the theory in that particular material. Are there questions on exam 2? It should be consistent with exam 1 in terms of the process. Topics obviously are a little different. As a recap, let's start with this notion of an adjoint operator, and the symbol that we were using is this superscript dagger, and I usually just say T dagger to mean the adjoint. T dagger is such that the inner products are equal between TV, comma W and V, comma T dagger W. We essentially are defining the adjoint so that we maintain equality between those inner products. And the adjoint is obviously going to depend on the inner product. And we can define the inner product many different ways for different vector spaces. Where T is a linear map between V and W, and T dagger is then going in the other direction from W to V. Which I've said before, this idea of an adjoint is, how do you move this linear operator or linear map? I shouldn't say operator because it doesn't have to be an operator. It could be a linear map. How do you move this linear map from one slot of your inner product to the other slot? And the process of doing that, or what you end up with in the other slot, is what can then be defined or used to define your adjoint operator. That's sort of a intuitive way to be thinking about this adjoint. Self-adjoint operators. This is now basically saying, when is T equal to, when is a linear map equal to its adjoint? And for that to make sense, these linear maps can't be going between different vector spaces. They have to be being operators, they have to go from back into where they came from. That's why we're now following that self-adjoint with the descriptor operator. So these self-adjoint operators, let's just look at an example. Suppose that we have the linear map T on this 2 vector xy producing another 2 vector that is ax plus by and cx plus dy. Now, we've talked about these adjoints and their matrix representations. There is a caveat. When we say the matrix representation of the adjoint is the conjugate transpose, complex conjugate transpose, that's only true when we were dealing with orthonormal basis. If we have something other than an orthonormal basis, then that complex conjugate transpose of the matrix representation no longer is necessarily true. Typically, if we're dealing with the standard basis, those are orthonormal, and the fact that we have the standard basis, we sort of lose track of that particular necessary condition. But it's necessary that our bases are orthonormal in order to make this adjoint matrix representation be the complex conjugate transpose. Now, you should by Wednesday be very comfortable with finding the matrix representation of that linear map. That is now this 2 by 2 matrix A, B, C, D. And that linear map then, when applied to the vector xy, gives us the new 2-vector ax plus by and cx plus dy in the second coordinate. Now, because we are dealing with these orthonormal basis vectors, we can now find the matrix representation of T dagger, or the adjoint of that linear map, by simply taking the complex conjugate transpose of A, and I'm just calling that B, to give us something different to talk about. So now we have a map, operator T, and its adjoint. If we want those, well, first let's just say that we have the adjoint's linear map representation. That's now A star x plus C star y in the first coordinate and B star x plus D star y. If we want these maps, or this map, to be self-adjoint, we need T, that linear map, to equal T dagger. And if that's the case, now what we're trying to do is make A equal B as a matrix. And if A equals B, then we need A and A star to be the same. We need D and D star to be the same. And if A is equal to its complex conjugate, what does that mean about A? It has to be real. And D then also has to be real, and that's what I'm trying to conclude here. If that map T is self-adjoint, then A equal to A star and D equal D star says these diagonal elements on that matrix representation of the linear map are real. And if you go back to those two matrices and look at those, you'll see that B is equal to C star or C is equal to B star says that the off-diagonal elements are complex conjugates of one another. And that's a way of thinking about this notion of a self-adjoint map for a 2x2 example. Let's then start writing, by talking about this general form of a self-adjoint operator. And let's do that by looking at the matrix representation of this linear map. And hopefully I can fit what I need into that big box. Now we know if it's self-adjoint, it needs to be the same size or the same height as it is width. It's square. And let me just say that I have A11, A12, A13, let's say A sub 1, N minus 1, and A sub 1, N. Now, if it's a self-adjoint operator, and this is the matrix representation of that, what does that mean about the first column? Or what maybe the easiest is, let's worry about the diagonal first. I don't know if I want to do this or not. I don't know if I'm going to be able to fit my stuff in right, but we know that along the diagonal, we can have unique numbers. And we'll basically say what we need on those, but we need those diagonals. What did we see in the 2x2 case? They have to be real, don't they? All of those numbers on the diagonal have to be real. So let me say with the A sub i's, real. Now let's worry about some of these off diagonals. What do I know about the first column if I've already written down the first row in terms of these A's? Or what do I know has to be true with that particular entry, the 2-1 entry? Do I know anything about it? What is it supposed to be? It's the complex conjugate of A12. So this is now A12 conjugate. We could do A13 conjugate, and I could just keep going down this column consistent with the top row, since the transpose of that will give me the first column. And now that's the complex conjugate transpose of the top row. And I could do the similar thing if I now keep the upper, or the elements above the diagonal, with the unconjugated versions. I knew I would be a little bit sloppy, but now I think you get the idea, where all of these keep repeating or looking with the same structure. But this is now A sub 2, 3 conjugate, A sub 2 n minus 1 conjugate, A sub 2 n conjugate, etc. Where this is now A sub n minus 1 n complex conjugate. If we have then a self-adjoint operator, then we have this structure for the matrix representation of that operator, that linear operator. And this particular structure for the matrix representation of that linear map is true for any basis. So this is now A sub II. Those are the diagonal entries. So this is the, with the A sub i's real. And that's now on the diagonal. Those entries are real. And now we're saying that this form for that matrix representation is true for any basis. And if we even specialize this a little bit more, to where now if we had a diagonal matrix, this diagonal matrix has this structure as long as what? What do we know about those entries on the diagonal? If it's self-adjoint, they have to be real. So a diagonal matrix has this structure if the diagonal elements are real. So let's look at this from a very simple perspective, just to try to get a little bit more insight into what we're dealing with when we're talking about these adjoints and self-adjoint maps. Let's examine a simple map and see how the concept or these concepts might generalize. where now we want a simple example showing that the matrix representation of an adjoint is the complex conjugate transpose of the original map. Or we're trying to show that this matrix representation of T, dagger, is in fact the matrix representation of T transposed and complex conjugated. That's what we want to see is true for a simple map. Or can we sort of show this by looking at a simple map? Suppose that our linear map T is between C and C. And really all that means is if I have a linear map operating on X, which is a complex number, a scalar, then let's just say that that's equal to a scaled version, where my scalar is also a complex number. A could be real or complex, but let's now keep it complex. And X is also complex. And we are wanting to generalize this or see how it might generalize, and for that reason, let's think of A not necessarily as a scalar, but as a matrix, where that matrix is now 1 by 1. So this is now a 1 by 1 matrix that's a scalar, because we now want to generalize this or think about it in terms of an n by n complex matrix. This is now a complex scalar or a complex 1 by 1 matrix. If my linear map T on X is AX, what's the matrix representation of T? If I now created a matrix that's going to correspond to this linear map, AX, what's the matrix representation? That's just A. So there's our A, and now A is, in general, a complex number. So now, if we have this linear map, or the matrix representation of this linear map, let's see what happens when we apply the definition of an adjoint and try to find the matrix representation of the adjoint operator of this. Let's apply the definition. of the adjoint to see what the matrix representation of the adjoint of this 1-by-1 matrix, what that looks like. Now, what's the definition of our adjoint? Or how did we define the adjoint? As a couple of inner products, didn't we? So if we now have T, let's say X, with V, by the definition of the adjoint, that should equal X with T dagger V. That's the definition of the adjoint. And let's go ahead and use the Euclidean inner product. And now what did we say? Well, now we have Tx, and the Euclidean inner product applied to this left-hand inner product means that we'll multiply Tx times what? T of x. If we were doing the inner product of two vectors that were complex, and let's say the first vector was x and the second vector was y, then we would be basically somehow multiplying component y's, but don't we do something a little different to y? Take its conjugate, don't we? So now we need to take the complex conjugate of v and use that to multiply T of x. And if that's the case, what do we get on the other side? We have x, and then we should have T dagger V complex conjugate. So that's just applying the Euclidean inner product with that definition of the adjoint. But what did we say that T of x was? That's just A times x. And so this is now times V star. But that's now equal to x times, well, T dagger, let's say we don't know what that is, but we know it's going to be some scalar B times V, and then we'll complex conjugate. So this is, for now, some unknown scalar. That's the B. But this is now for scalars, if we conjugate, that's B star V star. And since those are all scalars, they commute, and now we can say that we have B star times X V star. And now what we can hopefully see is that we have those two pieces are equivalent on either side of the equality, and now we can conclude that A must equal B star, or B is equal to the complex conjugate of A. And we said that B was our scalar associated with this adjoint, And now that says that if we take the adjoint of V, that's going to be BV. We just said it was some unknown B, but now we know what that unknown B is in terms of the original linear map T. That's just the complex conjugate of A times V. And using our reasoning that we used for the matrix representation of the linear map, now the matrix representation of that adjoint is going to be the complex conjugate of A. Which allows us then to say that the adjoint of a map is the generalization of the complex conjugate of a complex number. So now when somebody says, oh, what's the adjoint, you can start thinking, well, if I had a complex number as my map, now the adjoint is just the complex conjugate of that number. What if we had a self-adjoint map? If we use the same example, a self-adjoint operator says that T must equal its adjoint, which in our example we had A and its adjoint was A star. We need those to be the same, which now says that that number, for it to be self-adjoint, or that map for it to be self-adjoint, needs to be a real number. This now allows us to create this table that shows the generalization of numbers to maps. What I'm trying to suggest then is that if we have a number z equal to, let's say, a1 plus jb1, a complex number, then that we're just going to associate with a linear map. So this is now T is a linear map. But what if we now looked at the complex conjugate of that same complex number? We now have A1 minus JB1 If Z was a linear map, what's Z star? What did we just conclude that was equal to? That's now T dagger, isn't it? That's the adjoint map. And the last of our associations was if we had now Z equaling just A sub 1, or a real number, what kind of a map did that translate into or generalize to? That's a self-adjoint. Now our map T is a self-adjoint map. And that's now how you can start to think about these maps in terms of something very simple to try to gain some insight into what's maybe going to happen or take place relative to how do I start to get a feel for what's going on with these linear maps, these adjoint maps, and these self-adjoint maps. I'll look at some proposition and corollaries for these self-adjoint maps. And these are now coming from the second edition of the book. Proposition 7.1 says that every eigenvalue of a self-adjoint operator is in fact a real number. And that sort of goes in line with that last line. If we just boiled it down to a one-by-one matrix, we know that the eigenvalue is that matrix, or I'm sorry, yes, that number, which is real. Now we're just saying, oh, if we now have a bigger map that's self-adjoint, or an operator that's self-adjoint, and if we looked at the eigenvalues, every one of those eigenvalues is real. Let's sort of convince ourselves of that by stepping through a proof. Suppose now we have this linear operator T, and we're told that T is equal to its adjoint. It's a self-adjoint map. And now we need to show that the eigenvalues of T are real. If we're interested in eigenvalues, now as a review for Wednesday, what's the eigenvalue-eigenvector relationship for a linear map T, or a linear operator T? Now, you could use many different things. Suppose the eigenvector is V. Then we have TV is equal to lambda V. That's our eigenvalue-eigenvector equation, where lambda is the eigenvalue and V is the eigenvector. That's now what we will use. Let's now look at the following. Suppose that I look at scaling the norm of, or the norm squared of that eigenvector by lambda, the eigenvalue. What's another way of writing this norm squared we've been using? That's the inner product of the vector with itself. I can now say that's lambda times the inner product of V with itself. This is just the definition of the norm. But now I can actually slide that scalar inside the inner product to either of the slots, but let me just put it into the first slot. And how does it go into the first slot? Like itself, or do I have to conjugate it? In the first slot, we just have homogeneity, don't we? So we have lambda V, comma V. And this is just the homogeneity of the first slot. But I know that lambda and v are the eigenvalue and eigenvector, this linear map, which means if I start with that rightmost inner product, I can say that that's equal to, using the eigenvalue eigenvector equation, lambda v is the same as tv. So now I'm just going to abbreviate eigenvalue and eigenvector by eigenv. That's the eigenv equation. But now if I use the adjoint definition, what does tv comma v turn into? The definition of the adjoint just says I can slide the linear map into the other slot to create the adjoint. But now if I know that T is self-adjoint, what's that mean for the next line? I can replace T dagger with T, so that now if I go back and use the eigenvalue eigenvector equation again, I've now slid lambda into the second slot by using the eigenvalue eigenvector equation. But now if I want to pull that outside the inner product, now what happens to lambda, that scalar? It has to come out as the conjugate, doesn't it? So that I now have lambda star VV, and that's the conjugate homogeneity of the second slot. But the inner product of V with itself is just the norm of V squared. And now, maybe it's forgotten what I did up above, but I now started with lambda times the norm of V squared, and I've shown that that's the same as lambda star times the norm of V squared. I've now shown that lambda norm of V squared is equivalent to, for what? What did we assume on T? That it was self-adjoint. That's equal to lambda star V squared. And what was lambda and what was V? Lambda was the eigenvalue and V was the eigenvector. So that now we can say that lambda must equal lambda star, since the norm of that vector squared is the same and it's non-zero. We can divide that out. And if lambda is equal to its complex conjugate, now we know that all of the eigenvalues of that self-adjoint map are in fact real. Let's look at a few more propositions and corollaries from the book, and I'll refer you to the book for the proofs. We just talked about proposition 7.1. Obviously, then the next one must be something a little bit beyond that. It's way up to 7.2. Proposition 7.2 says that if V is a CIPS, And I assuming that these are clear when you tweet these out or when you text these, this CIPS, what is that? Complex inner product space. So now V is a complex inner product space, and let's say that T is a linear operator on V. And suppose that that linear operator, applied to a vector V, an inner product with V is equal to 0 for any V in our vector space. As long as we're dealing with a complex inner product space, then we can actually conclude that that linear operator is in fact the 0 operator. So that's proposition 7.2. If V is a complex inner product space and T is a linear operator, and for all V in the vector space, V's inner product is 0, then we can say that that linear operator is in fact the 0 operator. Corollary 7.3. Suppose that V is a complex inner product space and T is a linear operator on V. Then T is self-adjoint if and only if the inner product of TV with V produces a real number for all vectors V in our complex inner product space. So that now if you're computing something and you know that T is self-adjoint and you make a computation of the inner product and it comes out complex, or to be a complex number, then you know that you've maybe made a algebra mistake or some kind of computational mistake. Proposition 7.4. If T is a self-adjoint operator on V, such that TV inner product with V is equal to 0 for all V on V, then that linear operator is in fact the 0 operator. What's the difference between this proposition, 7.4, and 7.2? 7.2 says V is a complex inner product space and T is a linear operator such that TVV equals 0. For all V, then T is 0. 7.4 says if T is a self-adjoint operator on V such that TVV is 0 for all V, then T is equal to 0. What's the difference? What are we assuming? What are we not assuming? In 4 or 2, what's the difference between these? Did we say anything about V in 7.4 as far as what kind of a space it is? We know it's an inner product space because we're using an inner product in the statement of the proposition. But we didn't say that it was complex. Now it could be real. But what's the restriction on this linear operator T in 4 versus 7.2? In 7.2, we just needed it to be a linear operator. We didn't say anything about its more demanding characteristics. Now in 7.4, we're saying that operator is self-adjoint. So the operator is equal to its adjoint in 7.4. Proposition 7.4 extends Proposition 7.2 to real inner product spaces, but adds the requirement or the constraint that now this operator needs to be self-adjoint. Let's now see why we need that. Or why do we need this linear operator T to be self-adjoint when dealing with real inner product spaces? Let's just look at an example to maybe give us some insight. Suppose that we start with a real, non-zero, linear map that actually has TV, V equaling 0 for all V. So if we can find that, then if it's non-zero, then that's why we might need this self-adjoint characteristic of that linear map. Suppose we let V be R2. And now let's just say that Txy, this linear map, is beta y minus beta x. What's the matrix representation of T? What's the top row? 0 beta. And what's the bottom row? Minus beta 0. Do you recognize, or if you have some experience with eigenvalues and matrices, does this structure hint to anything about the eigenvalues of that matrix? Pardon? So these are purely imaginary, aren't they? These eigenvalues are purely imaginary. And they're at plus and minus j beta. Or this maybe looks somewhat like a rotation, doesn't it? Now we have this point xy, and x now becomes beta y, and y becomes minus beta x. Now, is this map self-adjoint? Is T self-adjoint? What's it need to be self-adjoint? The diagonals need to be real, passes that test, but what else do we need? We need the off diagonals to be complex conjugates. Is it? No. So this particular map, notice T, is not self-adjoint. And because of that, then is T non-zero? It's a non-zero map, isn't it? We're actually populating something in the first coordinate and the second coordinate of the output of that. If we start with an xy, then that linear map is not the zero map. What happens when we look at the inner product of the linear map T with xy applied to xy? T applied to xy was minus, or what was it? Was beta y and minus beta x. And now we want to multiply or inner product that with xy. Which now gives us beta yx minus beta xy, and x and y and beta are all scalars. This is now 0. And that's going to be true for all x, y, and beta that are real. Which means that we can create linear maps that are non-zero such that the inner product of TV with V for any V can be 0, and that doesn't mean that the map itself is the 0 map. So it's critical in proposition 7.4 that we have this self-adjoint property of that linear map in order to make this conclusion that the map T is equal to 0, or the 0 map. This example is trying to then show a case that violates that, but it violates that because we're assuming that it's, well, we created this map that was not self-adjoint. Let's now start to look at normal operators. Not that we need abnormal operators, but this is now a new term, a normal operator. A normal operator and that normal is mainly because of the norm is where that word's coming from, not abnormal, but normal. A normal operator on an inner product space is one where the linear operator T commutes with its adjoint T star, or T dagger. That is, T dagger is equal to T dagger T. If we have a map times its adjoint equaling its adjoint times its map, then that's a normal operator. it should be clear that all self-adjoint operators are normal operators. If a map is self-adjoint, we know T is equal to T dagger, which that says that T dagger is just T times T. But if T and T dagger are the same, I can say, oh, T is T dagger, and now I have T dagger is equal to T dagger T, or if we have a self-adjoint operator. The other direction is not necessarily true, though. Normal operators can in fact include non-self-adjoint operators. Let's look at an example. So Axler gives an example of a linear operator T with the following matrix representation. Suppose that this matrix representation of the linear map T is 2, minus 3, 3, 2. Is that a self-adjoint map? No, the diagonals are real, but the off-diagonals are not complex conjugate. So this is not self-adjoint. What's the linear map of that T translate into? If I now said T of xy, what's T of xy? Two x minus 3y and 3x minus 2y. Just making sure you're awake. Plus 2y. 3x plus 2y is the second coordinate. Now, what's the matrix representation of T dagger? The matrix representation, if we're dealing with orthonormal basis, is just the complex conjugate transpose. This is real, so now the 3's just change places. So we now have 2 minus 3 in the first column and 3, 2 in the second column. And let's call that B. And if we wanted to, we could find that linear map, T dagger of xy is now 2x plus 3y, and in the second coordinate, 3x plus 2y. What's AB if we multiply those together? A was 2 minus 3, 3, 2. And B was 2 minus 3, 3, 2. so that the first column is twice the first column and minus 3 the second column, so that we now have 4 plus 9 in the 1, 1 entry, and in the 2, 1 entry, we have 6 minus 6, or 0. In the second column of our product, we take 3 times the first column and 2 times the second. The 1, 2 entry is again 6 minus 6, or 0, and the 2, 2 entry is 3 squared plus 2 squared, or 13. Now, what's BA? That's going to be the same thing, but let's go ahead and show that. There's B, and here's A. Now we scale the first column by 2 and the second column by 3, and we get 13. And we get minus 6 plus 6 to give us 0. And the second column in the product is going to be minus 6 plus 6, or 0, and 9 plus 4, or 13. So now we see that those two operators commute by multiplying their matrix representations, but that linear operator was not self-adjoint, but it is normal. That linear operator is normal, but not self-adjoint. A being equal to 2 minus 3, 3, 2, is not self-adjoint, but that A of 2 minus 3, 3, 2 is a normal operator. Proposition 7.6. Say we're starting with an operator T on V, and now we're going to say that operator T is normal if and only if the norm of TV is equal to the norm of T dagger V. So this is sort of where this norm is coming from in normal. The normal operator is such that TV's norm is equal to T dagger V's norm. If we know that T is normal, what's another way of writing that down? We know that T commutes with its adjoint, don't we? So we know that T dagger is equal to T dagger T. Well, let's just rewrite that a little differently. Suppose that we now have T dagger T minus T dagger. That's equal to 0. Now, suppose that I take the inner product of T dagger T minus T dagger operating on V with V. But that is just because T is normal, that's equal to 0, and the 0 vector inner product with any vector is 0. And now we can do what? Let's play with the additivity property in the first slot. Additivity of the first slot says that we now have T dagger T, V with V, minus T dagger V with V, and that's equal to 0. Say for all V in V. And now we can start using our definition of the adjoint, where now we have T dagger applied to TV and T applied to T dagger V in the first slot. But if we use the definition of the adjoint in both of those instances, what do we end up with in the first inner product? We want to slide that T dagger into the second slot, so we now need to dagger that dagger in the second slot. We now have TV, and we have T dagger dagger times V to move it over into the second slot. And if we're taking T into the second slot, we now say that that's T dagger V. And again, that's equal to 0. What did we learn that T dagger dagger was last time? That's just T. So that now we have TV inner product minus T dagger V T dagger V equaling 0. And those are just the definition of the norms. We now can see that TV's norm squared is equal to the norm squared of T dagger V for all V in V. So you could basically play that tape forward and backward to give us our if and only if, which we started with sort of at the start, saying that T normal implies T dagger T minus T dagger equals 0, or that right-hand side implies that T is normal. And then we just sort of followed the logic down so that now we can see that if we have a normal operator, it's fallen asleep on me again, then these norm squareds are equal. Observation: the operator T dagger T minus T dagger is self-adjoint. Now, we didn't say anything about T being anything, and we didn't say anything about it being normal. We're just saying that if we just have T dagger T, or T, then T dagger T minus T dagger is self-adjoint. Which means that if we look at the dagger of all of that, we better get back what's inside the parentheses if it's self-adjoint. And this now is a linear operator, so we can say T dagger T daggered minus T daggered daggered. And what happens when we dagger a product? We reverse the order of those operators, don't we? So that now we have T daggered operating on T dagger dagger minus T dagger daggered operating on T dagger. So that now we have T dagger T minus T dagger, and that's actually what we started with in the parenthesis above, so that now we have shown that that operator is in fact self-adjoint. And we'll pick up at that point in a week after exam number 2, which is Wednesday. This Wednesday is exam number 2.